Now we'll come to the section B. And the first question is, let f be a function from domain S to codomain T. So we have this function f defined from S to T. And then we have this function g, which is defined from T to U. Now we need to fill in the blanks. Now the first condition is, if g of f is 1, 1, then. Now if g of f is 1, 1, it simply means g of f x1, it must be equal to g of f x2 whenever x1 equals x2. Now in this case, if f is 1, 1, then from fx1 equals fx2, we'll get this condition that x1 equals x2. And if we take composition of g, we can write g of fx1 must be equal to g of fx2. So if fx is 1, 1, then it's a sufficient condition for g of f to be a 1, 1 function. So if g of f is 1, 1, then we have this condition that it must be 1, 1, but it need not be on 2. So we'll have this b here, and this g, it can be any function. So it need not be 1, 1 or need not be on 2. So here we'll have b and d. So these are very standard conditions for composite functions. Now the second one is, if g of f is on 2, that means g of fa, it is equal to b, then clearly this function g, it has to be an onto function. So this g, it must be an onto function. So we'll have this condition c here, and if g is onto, then this function f, it can be any general function. Then we have this general condition d. So the answer to this question is b and d for the first one and d and c for the second one. Now the second part of question 1 is, we have this square whose length is, suppose, x, and points x and y respectively on sides BC and CD such that x lies on a circle with diameter AD. So that means this angle is 90. If this angle is 90 and this is suppose theta, it will be 90 minus theta, and again it will be this theta. Now it says AX is 4, so this is 4, AY is 5, then this value, it must be 3. Now these two triangles, XBA and YCX, they are similar. So from here we can write x upon 4 will be equal to cx upon 3. So this cx, it is 3x by 4. So this value is 3x by 4. So this bx will actually be x by 4. Now this right angle triangle, we have x by 4 and 4. Using Pythagoras, we can write x square plus x square by 16 will be equal to 16, or 17x square equals 16 square, or x square is simply 16 square by 17, and this x square is actually nothing but area of this square, which we need to find. Now here the question is, a mother and her 2 daughters participate in a game show. At first, the mother tosses a fair coin. If the result is heads, then all 3 win individual prizes and the game ends. And if the result is tails, then each daughter separately throws a fair die and wins a prize if the result of a die is 5 or 6. Now first, mother tosses a coin, and if she gets heads, then all of them, they win. And if it is tails, then both the daughters, they roll a die, and if they get 5 or 6, they win, else they lose. So for both of them, we'll have these conditions. Now getting a heads, it is 1 by 2. Getting a tail, probability is 1 by 2. Daughter 1 winning, her probability is 1 by 3. Losing is 2 by 3. And the same way for second daughter, it will be 1 by 3 winning and 2 by 3 losing. Now the first question is, suppose the first daughter did not win a prize, then what is the probability that second daughter also did not win a prize? So we need to find this conditional probability that second daughter did not win a prize when first one did not win. So we'll have this probability as probability of D1 intersection D2 upon probability of D1. Now both of them, they'll not get a prize only when if it is tails. So if it is tails, we'll get 1 by 2, and then both of them, they independently do not get 5 or 6. So it will be 2 by 3 into 2 by 3. Now divided by probability of first daughter not getting a prize. Again, it will be this 1 by 2, and she won't get a prize if the probability is 2 by 3. So we'll cancel. So answer to this first part is simply 2 by 3. So if first daughter did not win a prize, the probability that second daughter will also not win a prize is 2 by 3. Now in the part B it says, suppose the first daughter won a prize, what is the probability that second daughter also won a prize? We need to find this probability that second daughter wins the prize if first one wins the prize. So it will be this probability W1 intersection W2 upon probability of W1. Now probability of W1 is either when we get heads, so it will be this 1 by 2, or when it is this 1 by 2 and she gets 5 or 6, so it will be this 1 by 3. And the case when both of them wins, it could be this first case when it is 1 by 2, or the second case when they get tails, both of them they won a prize, so it will be 1 by 3 into 1 by 3. Now this 1 by 2 will cancel, so we'll get this as 1 plus 1 by 9, and there will be 10 by 9 divided by, now this is 1 plus 1 by 3, and there will be 4 by 3. Now this is 3, it will be simply 5 by 6. So the probability that second daughter also won a prize, provided first daughter wins it, is 5 by 6. Now for the second part A, we need to prove or disapprove 2 to the power 40 is greater than factorial 20. Now one way of doing it is using Stirling's formula. So we can show that this factorial 20, which is factorial n, it can be approximated by n to the power n e to the power minus n into under root of 2 pi n, and in this way this factorial 20, it can be approximated to the power 2 to the power 60, which is much greater than 2 to the power 40. That means this statement A, it has to be false. Now one way of proving it is, we can write this factorial 20 as 1 into 2 into 3 4 into 5 into 8 9 16 17 up to 20. Now we know that 3 is greater than 2, so we can write this expression is greater than 2 into 2 will be 2 square. Now 5 is greater than 4, 6 is greater than 4, and 7 is greater than 4, so it will be greater than 4 to the power 4. In the same way, 9 is greater than 8 up to 15, so it will be 8 to the power 8, and then we'll have this 16, 17, 18, 19 and 20, so it will be 16 to the power 5. Now this is 2 square, 2 to the power 8, 2 to the power 24 and 2 to the power 20, which is 2 to the power 54. So whatever the value of factorial 20, it will always be greater than 2 to the power 54, and therefore it is always greater than 2 to the power 40. So this first one is definitely false. So for this first part, we'll assume a function f(x), which is 1 minus 1 by x minus log x for all x greater than 0. Now we find f dash x will be 1 upon x square minus 1 by x, which is 1 minus x upon x square. Now its critical point is at 1. This is minus and this is plus. So this 1, it is a point of local maxima. And if 1 is a point of local maxima, then f1 will be greater than or equal to fx for all x greater than 0. Now f1 is 1 minus 1 and log 1 is 0. So 0 will be greater than 1 minus 1 by x minus log x. So from here we can say 1 minus 1 by x will be less than or equal to log x whenever x is greater than 0. And for the other one, we'll assume another function, say gx, which is log x minus x plus 1 when x is greater than 0. Again we'll find g dash x, which is 1 by x minus 1, and again we'll have a maxima at 1. So for this function also, g1 will be greater than or equal to gx, and g1 here is 0. So again 0 is greater than or equal to log x minus x plus 1. So from here we can say log x will be less than x minus 1 whenever x is greater than 0. So combining these two, we can say this inequality is true for any x greater than 0. So this is always true. Now the third question is, you need to create a 7-character long password for your mobile device. Now how many 7 character passwords can be formed from the 10 digits and 26 letters? Only lowercase letters are taken and repeats are allowed. Now for this password, for each of these 7 positions, we have 36 choices each. So number of choices will be 36 into 36 into 36 7 times. So total number of ways of choosing this password will be simply 36 to the power 7. So answer to this first part is 36 to the power 7. Now the second one is, how many of these passwords contain at least one of 26 letters and at least one of 10 digits? We'll solve this question using inclusion and exclusion. So what we'll do is, from the total, we'll remove all those cases where passwords are either all numeric or they are all alphabets. So total number of passwords is 36 to the power 7 minus now number of passwords which are all numeric. Now if they are all numeric, then for each position we have 10 choices. So it will be 10 into 10 into 10 7 times. So we have to subtract this case. Or where the passwords are all letters, in that case for each place we'll have 26 options. So it will be this 26 to the power 7. So answer to the second case is 36 to the power 7 minus 10 to the power 7 plus 26 to the power 7. Now we'll come to this third case. How many passwords contain at least one of the 5 vowels, at least one of 21 consonants, and at least one of these 10 digits? So now we have 5 vowels, 21 consonants, and 10 digits. Now we need to form a 7-character long password containing one from each category. Now again we'll solve this using inclusion, exclusion. So what we'll do is we'll find total. Now total number is 36 to the power 7, and from this we'll subtract all those cases in which at least one is missing. Now if vowels are missing, then for each position we have 31 choices. So it will be 31 to the power 7 plus, now if consonants are missing, we'll have 15 choices for each position. So it will be 15 to the power 7, and plus if digits are missing, then we'll have 26 choices. So it will be 26 to the power 7. So this is NA plus NB plus NC minus NA intersection B. Now if both vowels and consonants they are missing, then we'll have just digits. So it will be simply 10 to the power 7. Now if vowels and digits are missing, just consonants, it will be 21 to the power 7, and then minus if consonants and digits, we'll have just vowels, and there'll be 5 to the power 7. And that is the answer to this part 3. And finally we have this fourth case when we have 5 vowels, 12 consonants, 10 digits, and 12 special characters. Now again we have to form 7-character long passwords so that it contains at least one from each. Now for this also, we'll first find total number of passwords that can be formed without any restriction. So here we have 36 plus 12, 48. So total number of ways of doing it is 48 to the power 7 minus all those cases in which at least one of them is missing. Now if 5 vowels they are missing, then we'll have 21 plus 12, 33 plus 10, that will be 43. So it will be 43 to the power 7 plus, now if consonants are missing, there will be 27 to the power 7. If digits are missing, there will be 38. 38 to the power 7. And if special characters are missing, there will be 36 to the power 7. Now this is NA plus NB plus NC plus ND. Now minus if 2 of them they are missing. Now we have to choose combination of 2. Now if vowels and consonants they are missing, then the password is formed with digits and special characters, and there will be 22 to the power 7. Now if vowels and digits are missing, then we have 33 choices. So it will be 33 to the power 7. And if vowels and special characters are missing, then we'll have 31 choices. So there will be 31 to the power 7. Now if consonants and digits are missing, then we'll have 17 choices. So it will be 17 to the power 7. And if consonants and special characters are missing, then we'll have 15 choices. So there will be 15 to the power 7. And finally, if D and S they are missing, then we'll have 26 cases. So there will be 26 to the power 7. Now once we have summation NA minus summation A intersection B, we'll have to add N A intersection B intersection C. So it will be plus, now if 3 of them they are missing, So if these three they are missing, then we'll have 5 to the power 7. If we just have consonants, then it will be 21 to the power 7. Only digits, there will be 10 to the power 7, and only special characters, there will be 12 to the power 7. And this is the answer to this question. Show that there is no polynomial px for which cos theta equals p sin theta for all angles theta in some non-empty interval. Now it says, in the first step, you may want to show that this cannot happen for two polynomials. That is, it cannot happen for f and g. Now suppose there are two polynomials for which it can happen, and say they are given by fx and gx. Then for all x, fx, it must be equal to gx. Or we can write this fx minus gx will be 0 for all x. Now it is only possible if it is an identity and it has infinite roots. And if it has infinite roots, then both the polynomials, they must be same. So we get this condition that fx and gx, they must be same, having same degree and same coefficients. Now if suppose we have this polynomial in which we have this p sin theta equals cos theta. Now we can write this cos theta is under root of 1 minus sin square theta. Now we can write p sin theta square will be equal to 1 minus sin square theta. Now if we take square of this polynomial, then leading coefficient, it cannot be negative with real coefficients. So that means there is no polynomial p possible for which we have p sin theta equals cos theta. So there is no polynomial px for which this is true. Now in B5, we are given this function which is defined as this improper integral from 1 upon x to infinite 1 upon t square cos t dt. Now in the first part, for any x greater than 0, we need to show why this improper integral converges. Now we look for absolute convergence, then we can write this mod fx will be less than or equal to this integral from 1 by x to infinite mod of 1 upon t square cos t dt, and mod cos t is less than 1, so it will be less than or equal to this integral from 1 by x to infinite 1 upon t square dt. Now value of this integral is minus 1 upon t from 1 by x to infinite. So this is nothing but this is x. So clearly this integral, it converges absolutely. So that's your first part. And the second part says find f dash 1 upon pi if it exists and clearly indicate the basic results you are saying. Now we are given this function fx, which is this integral from 1 upon x to infinite 1 upon t square cos t dt. Now if x is unequal to 0, we can use Newton-Leibniz formula. So we can write this as f dash x. Now this is minus and it will be 1 by 1 upon x square cos 1 by x, and here it will be minus 1 upon x square. Now this minus and minus, it cancel, and x square will also cancel. So we'll get f dash x as cos 1 by x, or we can write f dash 1 upon pi will be equal to cos pi, and cos pi is minus 1. So answer to this part 2 is minus 1. Now this third part is using the hint or otherwise find this limit h tends to 0 positive fh minus f0 upon h. Now in the question it says f0 is 0. So basically we have to find limit h tends to 0 positive fh minus f0 upon h, and it will be this limit h tends to 0 positive 1 upon h. Now f0 is from 1 upon h to infinite 1 upon t square cos t dt, and f0 is 0. Now we'll solve this question using by parts. So this is first function and this is your second function. Now we can write this as 1 upon h, and here it will be 1 upon t square sin t, and from 1 by h to infinite limit h tends to 0, and minus here will be this 1 by h from 1 upon h to infinite, here will be minus 2 upon t cube, and here will be this sin t dt. Now if we put t as infinite, it will be 1 upon infinite and oscillating value minus 1 to 1, so it will be 0. So here we can write this as limit, and it will be h sin 1 upon h, and we can write this as 1 upon h, and then this integral from 1 by h to infinite 2 sin t upon t cube dt. And this is actually h tends to 0 positive. Now if h is 0, it will be 0 into sin infinite, which is oscillating value minus 1 to 1. So this is 0, and we'll prove that this integral, it also converges to 0. Now again we'll use absolute convergence. So we can write mod of 1 upon h, this integral from 1 upon h to infinite 2 sin t upon t cube dt will be less than or equal to 1 upon h, and then this integral 1 upon h to infinite mod 2 sin t upon t cube, and again sin t is less than 1, so it will be less than 2 upon t cube dt. Now this is 1 by h, and it will be minus 1 upon t square from 1 by h to infinite. Now this is nothing but this is h, and when h tends to 0 positive, this integral also, it approaches 0. So in this case, this entire limit is simply 0. Now the sixth question, we have two positive integers n and k, and we have two stacks, stack A having n cards and stack B having k cards. Now in stack A we have cards from the set 1 to k, and stack B we have cards from the set 1 to n. Now t0 is 0, and if tj is less than or equal to 0, we draw a top card from stack A, which is tj plus 1 equals tj plus the number written on this card. And if tj is greater than 0, then we draw a top card from stack B, tj plus 1 equals tj minus number written on this card. And whichever the case, we discard this taken card and we continue. Now in the first part, we need to prove that for every j we have tj lying between minus n plus 1 and k. Now we'll prove this result using induction. Now if we look at t0 is 0 and 0, it lies between minus n plus 1 and k. Now let it be true for tj, that is tj, it lies in minus n plus 1 to k. Now using this, we'll prove tj plus 1 will also lie in this interval. Now we'll take two cases. Case 1, when tj, it lies between minus n plus 1 and 0. Now in this case, tj plus 1 will be tj and plus the number on this card. Now this number, it lies between 1 and k. Now smallest value of tj plus 1 is, when this value is smallest, minus n plus 1, and the smallest card, which is plus 1, and its maximum value is 0 plus k. So this tj plus 1, it will lie in minus n plus 2 and k, which lies in minus n plus 1k, which proves our result. Now we take the second case, when tj, it lies between 0 and k. Now here tj plus 1, it will be this tj minus n, and here this n, it will be a card from 1 to n. Now the smallest value of tj plus 1 is when ti is smallest, which is 1, and n is highest, so it will be 1 minus n, and its highest value is when tj is highest, which is k, it is 1. So this tj plus 1, it lies in the interval 1 minus n to k minus 1, and which lies in the interval minus n plus 1 and k. So for both the cases, this tj plus 1, it is greater than or equal to minus n plus 1 and less than or equal to k. So from induction, we can say that this is true for every j. Now the second part, we have to prove that there are at least two distinct indices I and j such that ti equals tj. Now for this, what we'll do is, we'll consider two cases. Case 1, when we suppose the game ends when we try to draw from stack B. So we have drawn all the cards from stack B. Now since stack B, it has k cards, so we have to try and draw at least k plus 1 times. And we draw from stack B if Tj is positive. So for each of these k plus 1 times value of Tj, it is positive. Now the first part, we have proved that the value of Tj, it lies between minus n plus 1 and k. So the positive values are from 1 to k. So we have only k distinct positive values. And if we have k plus 1 positive values, then at least one of the value, it must be repeated. So there'll be at least two different indices I and j such that Ti equals Tj in this case. In the same way, if stack A is empty, then we need to choose n plus 1 times from stack A. Now we choose from stack A if Tj is less than or equal to 0. And again, from this first one, total number of non-positive numbers is n. So here again, since we have n plus 1 non-positive numbers from n non-positive numbers, then at least one number is repeated. So again, in this case also, we'll have two different indices I and j such that Ti equals Tj. And the third part, it says, using the previous parts or otherwise, prove that there is a non-empty subset of cards in stack A and another subset of cards in stack B such that sum of numbers in both the subsets is same. Now in part B, we have already proved that there are two different indices I and j such that Ti equals Tj. And in between these steps, either we add the number written on the card in stack A or we subtract the number written on card in stack B. And since these two indices, they are equal, it means that the set of cards drawn at I plus 1, I plus 2 up to j, it must be 0. And if it is 0, then it means sum of positive numbers must be equal to sum of negative numbers. That is, sum of cards drawn from stack A must be equal to sum of cards drawn from stack B. And this is how we prove such questions.